All right, welcome to our first lesson for Chapter 7. Chapter 7 is all about populations, population ecology, human population, all of that. So for this lesson, we're going to do an introduction to population. So learning objective or learning goal is that you'll be able to describe basic population characteristics, including survivorship curves and population growth curves. So this is an introduction to populations, and we're going to talk about some of the graphs and ideas that we will then look back on in our later lessons. So there is quite a bit here, but it's gonna be great. All right, so brief reminder from a previous lesson. We talked about levels of organization in ecosystems, and one of the things that we talked about was populations. So a population is a group of individuals of the same species inhabiting the same area. So they are all the same exact species, they can breed, live together, all of that. But within that population, we still see genetic differences. So like both of these are black bears, but they are different colors. That is a normal thing that we see in many, many, many different populations. And it might not all be genetic like things that we see. It could also be resistance to disease, anything like that. There are varieties between individuals within the same population. Okay, so population characteristics. This lesson is going to be defining a lot of the terms that we need to understand for future lessons. So natality is the number of individuals added to a population through reproduction over a particular time period, and birth rate equals the humans born per 1,000 individuals a year. Because if we did for every individual, that would just be a large number, so we do per 1,000. That's per capita, usually per 1,000 as well. Mortality is the number of deaths in a population over a particular time period, and death rate equals human deaths per 1,000 individuals per year. When we are looking at different populations, different species, we will see different kinds of survivorship curves. And survivorship curve shows the proportion of individuals likely to survive to each age. There are 3 types of survivorship curves that can be recognized, and we will name them as type 1, type 2, and type 3. So these are those 3 types. So type 1 is species with high mortality in young. So the way that we're going to read these graphs is our y-axis here is the number of survivors, and then our x-axis is in age. So this isn't necessarily like over time, it's just how many individuals live to this age in this species. So we look at plants. Plants produce so many seeds. Think about how many acorns are on the ground, how many seeds every little flower and fruit has in it. So many of those seeds do not then grow into plants. So for plants, they have very high mortality in young. So we have 1 million that start, and then we're down to, less than 100 before we even really get to like age 1. Type 2 is going to be species with mortality equitable, which is the same among the age classes. So we get a very straight line down. So we might start with, and most birds are an example. We start with 1,000, and then we lose this many by age 1. We lose almost the same amount to age 2, almost the same to 3. It's a very pretty consistent line. And then we have type 3. This is where humans would fall. So species with mortality high only in old age. This isn't to say that none of them pass or don't make it beyond those younger years. It just means that if we look at how many individuals are dying at a specific age, it's much, much higher with an older age. So we also have mountain goats here, rams there. We have a little bit of a dip in that first year, and then it's pretty consistent. Some passing, but then when we hit, age 12, it's a pretty direct drop off. So much higher mortality in old age. So type 1, young, high mortality in young. As soon as they make it past whatever year, they are from 40 to 60 years, no one's passing there. And then type 2, it's pretty consistent, and type 3, we'll see that drop off in older age. All right, so we're also going to look at population characteristics. So population growth rate is the birth rate minus the death rate. So you can only grow as long as more babies are being born than individuals passing. So to see how much is growing, we're going to do birth rate minus that death rate. And in human population studies, it's often expressed as a percentage of the total population. So this is one graph. We looked at this before, if you were here when we learned about graphs at the beginning of the year. But this is the effect of birth and death rates on population size. So in Costa Rica, we have our deaths up here in the red, and then our birth rate down here in the blue. So Costa Rica has a lower death rate than birth rate. So we're going to see a population increase, and it's shown as a 5.5%. If we look at Hungary, they have a higher death rate than birth rate, so their population is decreasing. United States, we do have a higher birth rate than we do death rate. It's lower, so our population is increasing much slower, but it is slowly but surely increasing. Another population characteristic we'll look at as sex ratio. So this refers to the relative number of males and females in a population. The number of females is important because females determine the number of offspring produced in sexually reproducing populations. There are some individuals, or not individuals, but like organisms that are capable of asexual reproduction, meaning they don't need another individual. But for those organisms that require another individual to reproduce, it is typically the females that are setting that limit of production because they are creating the babies. And then age distribution is another one. Age distribution greatly influences the population growth rate because if you have a huge population, but they're all not able to reproduce anymore, they're beyond their reproductive years, then your population is not going to be able to grow. If you have a huge population and they're all really young, then you know that those that are young are going to grow up and eventually be reproduction age, and that population is going to grow exponentially. So in Kenya, we see rapid growth. So most of the population, so the way that we're reading this is, this top part is post-reproductive. These are the individuals who are 45 and older. They are less likely to be reproducing at that age because we're looking at humans here. This middle column is reproductive, so they are from age 15 to 44. That is when most human beings are able to reproduce. And then we have pre-reproductive. So these are from 0 to 14, not typically reproducing at that age. So Kenya is rapidly growing. Their reproductive population is a lot bigger than their post-reproductive population, and their pre-reproductive population is even bigger. So that's once this section of that pyramid just goes up, it's going to be more individuals reproducing, and then we're going to see more people, more babies in pre-reproductive stage, and then they grow up and it continues. So we see rapid growth there. In Italy, it's going to be the opposite. So most of their population is in post-reproductive and like upper reproductive age. But then if we look at their pre-reproductive age down there, it's very, very small. So those individuals are not going to, most likely are not going to reproduce enough to, match the width of this here. It's going to be less babies. And then in the United States, we are slowly growing. These are the baby boomers, lots of babies right there. But we are slowly growing, but not as much as Kenya. And we do not have negative growth. And we'll talk about why some countries see that in a future lesson. So another thing that we look at is population density. Population density is the number of individuals per unit area. So how many individuals live in whatever defined area, square mile, square kilometer, whatever it is. High population density injures all individuals within the population because they compete severely for necessary resources. As human beings, we have housing and technology and things that kind of decrease this competition. But if we're looking at species other than humans that are, live it out in the wild, if you have a ton of individuals in a really small area, even of the same species, they have to compete for every resource that's there. Space, water, food. So when it says that it injures all individuals, it means that it's not serving them. If you are constantly competing for your food or for resources, then someone or multiple individuals realistically are not going to be able to survive or at least thrive. So when we look at population density, we look at how different populations or individuals move. So there's a couple terms here we're going to define. The first is dispersal. So dispersal is the movement of individuals from densely populated locations to new areas. We've seen this with humans. During the Industrial Revolution, humans clustered to cities and we were super, super densely populated. And then with the invention of cars, we were kind of able to move away. So we dispersed. Emigration is movement from an area. You emigrate from somewhere to somewhere else. And then immigration is movement into an area. So immigrating into a new place, new ecosystem, new country. Another thing is a dispersion pattern. So we'll see this with different species disperse differently depending on how much they rely on each other, whatever it is. So we could have uniform dispersion where they're pretty evenly far apart. Random dispersion, which is usually less, not super, super likely, but random dispersion is they are just randomly placed places. And then we have clumped dispersion. This one is pretty common if we're clumping around resources. All right, the last big idea we're going to talk about in this lesson is the population growth curve. So the first thing we need to understand is biotic potential. And biotic potential is the inherent reproductive capacity of a species. And in more simple terms, it's the biological ability to produce offspring. So biotic potential is, are you able to have, like, is that population able to produce babies for that population to grow? Generally, the biotic potential is much higher than the number needed to replace parents because in many populations, especially organisms out in the wild, every offspring is not going to survive. And so parents, individuals have more babies than will survive in order to replace them. There is a natural tendency for increase. Even with all of the technological advances and everything that we have, even humans in many countries, we still see that increase in population because that's just what is expected. Okay. Our final idea here is this population growth curve. So on your notes, I'm asking you to draw that curve and label it, but you also need to define each stage. So the population growth follows a pattern consisting of a lag phase, an exponential growth phase, a deceleration phase, and a stable equilibrium phase. We're going to start with this lag phase right here. The lag phase is the first portion of the curve, and it's very slow population growth. It's lagging behind. Then we get to the second stage, which is exponential growth. And exponential growth is also known as the log phase. So more organisms are reproducing, causing accelerated growth. So we have that reproductive population is increasing. So then we get a lot more babies, huge population growth. And then we're going to hit the deceleration phase. And that's when the population growth rate slows as the death rate and birth rate come to equal one another. So as the population that was growing right here, those individuals start to kind of like age out and start passing, and our population starts to kind of even out. And we also will have limiting factors that are holding that population down because there's only so many resources available. And then at the end, we get to the stable equilibrium phase. The death rate and birth rate become equal and the population stops growing. This is an idealistic, like really nice, perfect little graph to show what does typically happen. When we graph actual numbers, it will kind of look like this, but it's going to be a little messier. Typically, we'll have like an overshoot where the deceleration goes a little further and then it dips back down to meet stable equilibrium. But this is the idea behind it. All right, if you have any questions, please let me know, and I will see you in the next one.